Excuse me. Okay. We're asked to compare essentially the potential energy you get from MGH with the potential energy you get by actually calculating the potential energy change, thinking of gravitational potential energy. Now, MGH is implicitly the gravitational potential energy relative to the surface of the Earth. Now, if you go far from the surface of the Earth, where in this picture R was the radius of the circle, and the circle represented the Earth, and then we went from distance R to distance R plus H. Well, the question then is, how do you get the change in potential energy between here and here using the accurate model? Okay, because of course we understand the gravitational force falls off between here and here. On this picture, the distance from the center of the Earth appears to about double the way people drew this picture, which means that the gravitational force is going to become just 1/4 as great, being a reciprocal square force. If R doubles, R squared quadruples, and the reciprocal of R squared, the inverse square, becomes 1/4 as great. So you're going to have 1/4 the force out here that you do here. If you just use MGH, you're going to get a much bigger result. Okay, so we've got this MGH, but what we have to do to compare this with what you get from the accurate result, we have to calculate the change in potential energy from here to here, taking account of the decreasing gravitational force. Now, the first thing somebody did was wrote down this integral here. Okay, that's quite a good attempt. It isn't quite right, but it's a very good attempt. You're integrating the gravitational force from R to R plus H. Well, that's what you do. You integrate the gravitational force from R to R plus H. The problem with this integral is that the gravitational force is not calculated at R plus H. Okay, it's calculated at R, and your limits here and your variable R look to be the same, but you can't have your variable out here on your limits. So we need to be a little more specific. Now, the thing I suggested then was, well, let's not call this little r and little r plus h, because you're integrating with respect to r. You're going to have an r at every point from here to here. So r is a variable. R is not a good thing to use for the radius of the Earth. So we get rid of a little of our confusion if we use r sub e for the radius of the Earth. Then we're going from this distance from the center to this distance, re to re plus h. Well, that's going to make our limits on the integral re and re plus h, and now things are starting to be a little more consistent notation-wise. Okay. The other problem, though, is that, well, we have to think about what this integral means to see what else is wrong with it. So what we want to do, and what we did in class, ask somebody to show me this interval and a typical increment, and they did. And we have a force on that increment and a delta r. The work done on that increment is the force times the delta r. And the force at a sample point within an arbitrary interval is going to be big G, big M, little m over r star squared. And then that is multiplied by delta r to get the work. And of course, then we want to put a negative sign on this because the force is in the direction opposite to delta r, so the product is going to be negative. Now, what's written down here, and I think I wrote this, obviously I wrote this, it's really kind of messed up. It's not right because of that negative sign. I didn't include the negative sign here because we were talking about this. And just because I didn't include it. Okay, I messed up. So I want to fix the signs on this. And then we'll continue.